Now we're getting into dirty details. So the goal of this session is to, allow you to write your data more effectively and read your data more efficiently by optimizing how you store your data on disk and how you write your data to disk. And so there's all the code that I'm drawing in these slides is directly from the tutorials that are in the advanced I/O section of the PyNWB tutorials website. So if you want to follow along or try out any of these things, just go to those tutorials and you will have the code right there. It's just easier for me to present it in the slides. So we're going to start with this tutorial on HDF5 dataset I/O. What that means is you can customize on an individual dataset level how it should be laid out on disk and what its properties should be. And so the first big thing that you can do is you can choose to chunk your data set, right? So when we write a data array, let's say a two-dimensional electrical series array to disk, it ultimately gets on your hard drive, it gets flattened into a one-dimensional data stream, right? But what that means is depending on how you serialize it, reading a row, let's say an electrode, can be very efficient. I just do one seek and I read that part of my electrode. But then reading a full time slice becomes very expensive because I have to now constantly seek, jump, and read in my data set until I've traversed essentially everything. So depending on how you orient your data, some operations are fast and some operations are slow, just because everything becomes a 1D data stream on the disk at the end of the day. And so with chunking, what you can do is you can break up that array into subblocks, right? And then they will be stored as individual blocks in the file. For you as an end user, the data array looks the same as before. When you go read from HDF5, it still looks to you like a two-dimensional array, and you request your data exactly the same way. It's just under the hood. The data is going to be broken up. And so with that, you can now say, hey, I want chunks that are aligned with my time axis, or I want chunks that are aligned with my electrode axis. And then you can optimize the read pattern for what your primary type of data access is. And then, typically what you want to do in practice is you want to have some form of a compromise where you block your data in both dimensions in some form, which means neither your reading for electrode at time is going to be perfectly optimal, but both of them are going to be at reasonable performance, and you're not having one particular pattern suffer too much. The other thing that chunking does is if there are blocks of data, let's say you have large blocks of missing data, as long as you don't touch those blocks on write, they're never being allocated. So let's say you have a time series and you have a block of NaN values in the middle. If you blocked it the right way, those NaN values will actually never be physically written to disk, but they will just be automatically filled with whatever fill value you specify. So in that way, you can also reduce data size. All right. So how does this work in PyNWB? So the way you use chunking is by wrapping your data arrays into a wrapper class called H5 data I/O. So you can create your NWB file as usual, and then instead of creating my time series just with my data array, in this case, my data array is just this example NumPy array of 1,000 by 10 values. Instead of handing that as my data array to my time series, I first wrap it with this H5 data I/O object. And in this case, all I'm saying is I want you to use chunking, and I want you to use your best guess for doing chunking. So you just say chunks equals true. And then H5Py will automatically determine what it thinks the best chunking will be. And then when you say max shape, in this case none, 10, what it means is you're telling HDF5, I want my first dimension, which is time, to be unlimited. You want to be able to grow that axis later on. And then 10 means I want to fix my number of electrodes, in this case, to 10. And that's all you need to do. Now your data is being chunked. You can also specify, and writing works as usual as before. You just call PyNWB HDF5IO and do your write. You can control what chunking you want to use. You can physically specify, I want my chunks to be 1,000 by 10 or whichever chunking is optimal for your data. The other thing that chunking allows you to do is that now you can use HDF5 filter pipelines. What that means is that HDF5 allows you to apply different data processing filters during the read and write process. So each time you read a chunk, or each time you write a chunk, these filters will be applied. And then when you read, they will be applied in reverse order. For example, that allows you to do things like compression. You can now say, take each data chunk that I want to read or write and compress it or decompress it automatically. So again, independent of which filters are being applied, the data to you when you read or write looks exactly the same. It's just you have this processing happening under the hood, which can then, when you apply compression, for example, will reduce your data size. To apply compression, again, the workflow is essentially the same. You create your PyNWB file, you wrap your data set, and now you specify in H5 data or your compression settings. So the default compression will typically be gzip with some compression level of 4. So gzip is mainly the default because it ships directly with HDF5 and is installed on all systems where HDF5 is available. So it's just a convenient option in that way. But there are other filters available as well that may be better for your data. And so if you want other filters that are not available directly with HDF5 by default, you can use dynamically loaded filter plugins. There is a convenient package called HDF5 plugins that you can just pip install, and it will provide you with a large number of additional data compressors, for example, such as BLOSK or ZSDD. And so the way you can then use it once you have installed these plugins is that you just load your filter plugin that you want to use. In this case, we have here the HDF5 plugin.zstd with a compression level of 3, and then you set that as your compressor, and then you need to tell HDF5 data to actually allow plugin filters. The reason being is that we want to make sure that you are aware that you are using a custom filter that may not be installed on all other systems, right? Because the person that you ship the data to also needs to be having that particular filter then installed in order to read the data. And so that's why that is an explicit process. But it is a great way to get access to more advanced data compression algorithms. Right, and so just a general word of caution, right? Chunking and I/O filters are a really great way to optimize your data, but they're also a great way that you can mess up performance in your data if you don't choose quite the right settings. And so there's just some general rules, right? Don't make your chunks too tiny, and because poor chunk size. If you take the example that we had at the beginning, if I align my chunks to be just perfectly aligned in time, and I say one complete time step should be a chunk, now reading a full electrode might be slow because now I actually have to touch every chunk in my data set, right? And so you need to be a little bit careful of how we set these things up. There's also, I here just talked about chunking and compression, but there's also other filters that you can have, such as shuffling and checksum generation and so on, that work exactly in the same way. So you can nowadays implement your own HDF5 filters. And you have quite a high level of control in those. And so this works through HDF5's virtual object layer. And, it's just a matter of how much effort you want to go through in terms of implementing these sort of filters. You effectively have complete freedom to do whatever you want on that layer. To the point some groups have written filters to not write to HDF5 at all, right? Where they want to do processing of data as directly as part of data acquisition. It's not in neuroscience spaces, it's in high performance simulation space. But whereas these simulations already used HDF5 for their I/O, instead of actually writing the data to disk where they don't have enough space anymore, we just take the write calls, we ship the data somewhere else, do processing, and then actually just write some derived data product. So you have very high flexibility in terms of what you can implement on that layer, but it's not necessarily a trivial exercise to implement them. You need to have a skilled C or C++ developer who understands HDF5 to really implement that sort of processing that you want to see as like a dynamic filter that does bandpass filtering or something like that. It's technically feasible, but it requires some skill. So you don't want to get super big. You don't want to have chunks of like a gigabyte in your file. But typically a few megabytes is a decent size for a chunk. But then there's also different settings for how you want to do caching of chunks in HDF5 as well as on the I/O system. So these kind of things can go incredibly deep in terms of technical detail, which is why it's part of advanced I/O, because optimizing these things to the very detail just involves so many different levels. If you say, I just want it optimized for my particular system, if you would take exactly that setup, it might not work on exactly the same way on a different system. But that's why typically we aim for these kind of compromised setups that, to be honest, in practice typically show good enough performance throughout these different cases, and cover, I would say, 90% plus of what the typical user needs. And if you really have a particular case where you say, I need to optimize the performance to the last little bit of detail, then there needs to be some extra effort to be put in at that point. These things, the effect of it, or the impact you see grows with basically dimensionality of your data, as well as how skewed your data is. Right, and so in things like an optical physiology, where I have, an image resolution that's much lower than my time resolution, right? I might have a stack of, tens of thousands of images, and my image resolution is much less than that. Then chunking has a big impact, because now I can actually localize my reads. Right? I mean, that's really what it typically comes down to with I/O, is how local can I keep things on disk, right? How far do I have to jump around, and how often do I have to jump around? Because the more I can keep it to the point where I do a single point seek, where I say, now here's where I'm disk, and then I can continuously read, the faster you're going to be. The more often I have to jump around, the more small blocks I have to read, the slower your performance typically gets, in particular when you're on spinning disk. It's not quite as bad when you're on a solid state drive, but even there, doing lots of jumps can become expensive. The good news out of the experiment is also that you typically can find a balance that is good enough for most cases. And it's this, where you have a balance between how do I chunk my image as well as my time. Yeah. The other thing I would say is typically as a starting point, right? If you know the full shape of your data beforehand, and it's setting just chunking to true and letting H5Py determine a compromise is at least a good start, right? It's not necessarily the optimal way to find a compromise, but it provides at least a good hint for you to which direction to go, from which to start optimizing from, right? And if chunking equals true gives you reasonable enough performance, at least then, you have a starting point. And then, as we learn more exactly of, what's optimal for different types of data, that knowledge then also trickles into the tools like NeuroConv, right, which will do these kind of settings for you oftentimes. And so that's why it's good to, use those tools as well. Let's move on to our next section, which is iterative data write. So iterative data write is there to allow you to write your data to NWB without having to load all the data into memory, right? If you want to convert, let's say, a terabyte size file, you don't have a terabyte of main memory, so you want to write that data in blocks, right? The same way we chunk the data now, you want to be able to write this data in chunks. Now, the difference there is that the chunks you want to write shouldn't be necessarily exactly the same size as the chunks the way you lay it out on disk in HDF5, but typically on write, you want to say, I want to write as big blocks as I can at a particular time. And then to avoid having like these very intricate patterns of very small writes, just big blocks of data as you can and write those in blocks. The way it works in PyNWB is you have this data structure called a data chunk, which describes the location of a data block in the file. So it contains the data, which is just the values of that subarray, and then it has a selection attribute, which defines the NumPy selection, so you can locate that chunk inside the array where it should be going. And then you have these data structures that inherit from abstract data chunk iterator, which is a class that simply iterates over data chunks and returns data blocks one at a time. And then when we call data write, when we provide those, the I/O backend will iterate over the data chunks and write them into HDF5 one block at a time. So you load your chunk, HDF5 will write it, then you can discard that chunk and load the next one and so on. There are a few functions that need to be defined here, which is, the iterate data and next functions, which return the data chunks. We need to define the data type and the maximum shape for the data set, as well as the recommended shape of the data and chunk shape. The difference here is, so max shape tells you how big can the data set become at the end, and the recommended data shape tells you how big do you want it to be when you initially allocate it. And in the typical case where beforehand, like in a data conversion case, what shape the data should be, your max shape and your recommended shape will just be the same thing. And then there's additional convenience classes to help you with some of the most common cases, which are data chunk iterator and generic data chunk iterator. So data chunk iterator just implements a buffered write along the first dimension of a data array, and then generic data chunk iterator is a bit more of a generalization of that. It's a semi-abstract version of an abstract data chunk iterator, so it implements a number of additional functionality to automatically handle the selection and buffering of region and resolving of compatibility between regions. And so users specify chunk and buffer shapes or sizes of the iterator, and then the iterator itself manages how to break the data up for data write. If you have any questions on generic data chunk iterator, you ask Cody. He added that particular functionality, and it underpins a lot of how the NeuroConv does its iterative write. And so when you implement a generic data chunk iterator, you implement the get data, get max shape, and get dtype methods, and then it will implement things like the iterator methods and stuff for you. Right? Why do I want to do iterative data write? There's a few different reasons. First one is things like data streaming. If that would come up, let's say if you're using it during data recording, for example, your data is not available yet, and so you can have data being generated as you write it, and therefore avoid having to cache all the data before you convert. The more typical case that we have is, converting very large data arrays where you don't want to load everything into memory. And then another case would be things like sparse data write, like if you have large blocks of missing data that you don't actually want to have written, then with this you can, chunk your data and then just never touch the data chunks that have missing data. And that will in turn make sure that these chunks are not being allocated on disk. So here just an example for iterative data write. We have a method in this case defined which returns us data chunk blocks of data for our array, and then we just wrap that function in a data chunk iterator, and from there on out we can use it as usual. So at this point our data chunk iterator just becomes the array that we hand to our time series, for example. Okay. Let me see. Where was this? Okay. You can also completely customize your data write for an individual data set. And the way that works is you effectively just tell us what data you want to allocate. So you can use H5 data I/O, and you tell us what shape the data should have, what the data type it should have, how it should be chunked, how it should be compressed. And you just set up the data set. You then use that H5 data I/O the same way we did it before, right? But at this point, I don't have any data yet from you. All we will do on write is set up that data set. And then after you've written the data, you leave the file open, and then from the data I/O object, you can directly get the data set that we generated for you, and then you can resize it, you can set the data value, so you can completely control how you actually populate the data, and then everything is in your hands. So at that point, you're using PyNWB to set up the entire NWB file structures, but how you handle that particular data set on write, you now have full control over. And so those are the two main options that you can customize the data write for you. All right, I think at this point I should hand it over to Ben, because otherwise we're going to run way too long. And if you have questions on parallel or modular storage, I'm more than happy to talk about that with you individually, or if you really want me to present it, we can present it during one of the hacking sessions.